Hello, my name is Ethan Chinnis, and this is Lab for bar magnets. The purpose of this lab was to measure the magnetic dipoles at various locations about a bar magnet and compare those fields to the actual theoretical magnitudes given via Biot-Savart's law, as well as compare it to the code. The result of this lab is that the field of the bar magnet depend on the distance r -3, which makes sense from the equations, and whether it's parallel, there's a multiplier of 2, or no multiplier for perpendicular. And the magnetic dipole of the whole thing was 0.9. So the physics principles involved are Biot-Savart's law is that a magnetic field can be related to a current of wire I, and the distance r -2, but we're multiplying by a unit vector, so it's really by r -3, and then also multiplied by r vector. And then the magnetic field is mu over 4 pi times 2 times mu naught divided by r cubed. And the magnetic dipole ends up being mu is equal to the area of the wire times I. And the equation of distance dependence, which is gotten from our graph later on, is ln of b, the magnitude of the magnetic field, is equal to the ln of k, which is the constant, b over 4 pi, plus the n, which is the power of the r, times the ln of r. The setup here is we downloaded a magnetometer app on our phone, and then we place the phone one time on the axis, and another time it would be up here at a 45-degree angle, so these distances are the same. And we measure the B fields and other data at these locations and we put it all into a spreadsheet to make a graph and calculate our mu. And the system is the bar magnet, and the surroundings is everything else, especially the Earth's magnetic field, which we had to calculate for and subtract, as well as other stray fields from technology such as like computers and stuff. Here's all the data we collected at the distances and the magnetic fields here, and the averages taken from the 3 measurements. And down here we have our D and our D perp, which are used later on in the code. We also have the By from the Earth, which we subtract, and then our end up B net down here 0.001, the magnitude of the total. And we get this graph here, which has this equation calculated, which is negative 1.5465x minus 12.274, which these two numbers right here will be very important in just a second, which are both derived from the straight line from the graph. And here they are right here. The slope is our r, and the y-intercept is the ln of k, which the magnetic field B is equal to k times r to the power of n, which in this case is 3, because our B parallel, which is on axis, is equal to mu naught over 4 pi times 2 mu naught over r cubed. So we can set this equal to krn, where n is equal to 3, and we can isolate mu, and we get mu is equal to 0.9. Here's the code for this lab. Right here we have creating the magnet of the origin with our magnitude of mu, which is 0.9, and then here is where we create the magnetic field for the magnet using mu and r, and the distance, which we had back here in the data, 0.148, it's right here. And these create the observation locations. There's 4 perpendicular ones on the x above and below, and then z and negative z, as well as parallel ones in front and behind it. And then these draw the arrows right here. And then d perp, which we calculated also from here, right there. And the observation location 45 degrees, d perp and d perp, which is the same distance x and y direction away to get a 45-degree angle. And then we simply calculate everything, and then here's the code, the results. We have our perpendiculars here, and also here. They're stacked, the 2 z's, but they should be going in the same direction, so they're overlaying each other. And then in front, behind and in front. And here's all the b-axis calculations and the perpendicular calculations, and then the d here, and then b at 45 is right here. It's a -5th, but it's 1.37 to the -5th, and the magnitude of b right here at 45 degrees. So you basically just take the magnitude of these two to get this. So some possible errors for this lab is the stray fields of surrounding technology, such as computers, because they do give off a slight field, even though it's not much, as well as inaccurate photo and magnet positioning with relative to the Earth, because there's human error involved there positioning perfectly correctly, as well as errors in the app, because in the instructions in the lab, the app is supposed to be a lot more accurate than the phone compass itself. However, it's still not 100% accurate. And some assumptions we made is that the bar magnet is a perfect dipole, as well as the magnetic field being 0 at very large distances. So if we had oriented our experiment not to calculate for the Earth's magnetic field would end up interfering with the bar magnet even more than it already did, which would make the experiment even more inaccurate. And if we were to stick two identical magnets together end to end, it would actually double the magnetic field, which means our distance would be much larger because a stronger magnet can be felt from farther away. And that is all.